Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating question. Can AI compress like a genius? It's a deceptively simple question that gets at the heart of how we understand intelligence itself.
Exactly. Think about it. Compression isn't just about zipping a file to make it smaller. It's about finding the underlying patterns, the redundancies, and eliminating the unnecessary noise. A true genius is at compression would understand the data on a deep level, right?
Well, that's assuming that deep learning and neural networks, the current dominant force in AI, are capable of that kind of understanding. I'm not entirely convinced. They're excellent at pattern recognition, sure, but do they truly comprehend the information they're compressing?
I agree to some extent. I think that the current deep learning methods are brute force. They require a lot of data. I suspect that something more is needed. Perhaps we need to think about how AI deals with spatiotemporal data. Perhaps the ability to model and understand transformations is important.
Okay, hold on. Let's unpack this a bit. So, the starting point here is what even constitutes genius-level compression. I think we all agree it's more than just lossless or lossy compression algorithms as we know them. The brain is incredibly efficient at compression, right? We remember the gist of a conversation, not every single word. How does it achieve that?
Exactly. And that's where I think deep learning is showing promise. Look at things like autoencoders. They learn to compress data into a lower dimensional representation, a latent space, and then reconstruct it. The fact that they can do that, especially with complex data like images, shows they're capturing something fundamental about the underlying structure. It's not just pattern matching. It's learning a more efficient representation.
I see your point, but I still think there's a fundamental difference. An autoencoder might be able to reconstruct an image, but does it understand the meaning of the image? Does it know that it's a picture of a cat or a car or a person? It's compressing the pixels, but not necessarily the semantics.
Right, it's lacking that higher level understanding. Think about how we recognize objects in different orientations, in different lighting conditions. Our brains are constantly transforming the visual input into a consistent representation. That requires a sophisticated understanding of spatial relationships and transformations, something that current AI, in my opinion, struggles with.
That's interesting. So, you're saying that the ability to effectively translate between different coordinate systems to understand how an object looks from different angles is key to true compression, because you are essentially only saving the important data and transforming that?
Yes and no. I agree that understanding spatial relationships is important, but I think deep learning is getting there. Consider convolutional neural networks, CNNs. They are specifically designed to recognize patterns regardless of their location in the image. They are, in a way, learning to be invariant to certain transformations.
But CNNs are still limited. They're good at recognizing objects, but they struggle with more abstract reasoning. For example, if I show a CNN a picture of a cat sitting on a mat, it can identify the cat and the mat, but it doesn't understand the relationship between them. It doesn't know that sitting on implies support or proximity. That requires symbolic reasoning, something that deep learning doesn't inherently provide.
Exactly. It's about understanding the rules governing those relationships, the underlying physics, the common sense. Deep learning excels at finding statistical correlations, but it often misses the causal connections. It's like learning a language by memorizing phrases without understanding the grammar.
So, we're talking about moving beyond just pattern recognition to something that incorporates knowledge representation and reasoning. Sarah, that sounds like you're advocating for a neuro-symbolic approach.
Absolutely. I think a hybrid approach, combining the strengths of deep learning with symbolic AI, is the most promising path forward. Deep learning can handle the noisy, unstructured data, the raw sensory input, while symbolic AI can provide the structure, the logic, and the reasoning capabilities. We need to build systems that can learn from data and reason about it.
I'm not entirely sold on abandoning deep learning. I think it's still evolving. Look at the advances in transformers and large language models, LLMs. They're not just pattern matching, they're generating text, translating languages, and even writing code. That requires a certain level of understanding, doesn't it?
But are they really understanding or just cleverly mimicking? They're trained on massive data sets, and they're very good at predicting the next word in a sequence, but that doesn't necessarily mean they grasp the underlying meaning. They can generate grammatically correct sentences that are nonsensical or factually incorrect. We've all seen the LLM hallucinations.
Okay, let's go back to our central question. Can AI compress like a genius? It sounds like we're all converging on the idea that true genius-level compression requires more than just efficient encoding. It requires understanding, reasoning, and the ability to translate between different representations. So, How can we get there? What are the key research directions we should be exploring?
From my perspective, it's about pushing the boundaries of deep learning. We need to develop architectures that are better at capturing hierarchical relationships, at learning more abstract representations. We need to find ways to incorporate more inductive biases, more prior knowledge into the models. And yes, we need more data, but we also need better ways to train the models to encourage them to learn more efficiently.
I think we need to focus on developing better neuro-symbolic algorithms. We need to find ways to seamlessly integrate deep learning with symbolic reasoning to create systems that can learn from data and reason about it. That means developing new knowledge representation schemes, new inference engines, and new ways to combine the strengths of both approaches. We have to break down the problem into simpler components.
I think the key is to focus on spatiotemporal reasoning. We need to develop algorithms that can understand and manipulate different coordinate systems, that can reason about objects and events in space and time. That might involve exploring new mathematical frameworks, new computational models, and new ways to represent knowledge. And we need to look at the brain for inspiration. How does the brain solve these problems so effortlessly?
That's a great point, Donald. The brain's ability to seamlessly integrate disparate types of information is remarkable. Visual, auditory, tactile, it all comes together. So how can we translate those principles of multisensory integration from neuroscience to AI design? How can we build AI systems that can effectively utilize different modalities of input, text, image, audio, to enhance decision-making and knowledge acquisition?
Yes, and I think that touches upon something crucial, the ability of the brain to make predictions. Predictive coding is a huge area in neuroscience, and I think it's incredibly relevant to AI. If we can build AI systems that are better at predicting future events, they'll be better at understanding the present and compressing the past.
But predictions based on what? Just statistical correlations or actual understanding of the underlying mechanisms. That's where the symbolic component comes in. If you understand the rules of physics, you can make much more accurate predictions about how objects will behave. A purely data-driven approach can only take you so far.
And those rules of physics, those causal relationships, are often expressed in terms of spatiotemporal relationships. Think about Newton's laws of motion. They describe how objects move through space and time. To understand those laws, you need to be able to reason about space and time in a sophisticated way.
Okay, so let's push this further. Otto, from a deep learning perspective, what specific architectures or techniques do you see as most promising for achieving better compression and understanding?
I'm really excited about the potential of graph neural networks, GNNs. They're designed to operate on graph-structured data, which is a very natural way to represent relationships between objects. Think about a social network or a knowledge graph. GNNs can learn to extract meaningful patterns from these graphs, and that could lead to more efficient compression and better understanding.
GNNs are interesting, but they still rely on data. What about approaches that explicitly encode knowledge? For example, knowledge graphs with associated inference engines. You could use deep learning to extract information from raw data and populate the knowledge graph, and then use symbolic reasoning to infer new knowledge and make predictions.
And how do you represent spatiotemporal information in a knowledge graph? That's the challenge. You need to be able to represent not just the objects and their relationships, but also their positions in space and time, and how those positions change over time. Maybe we need to think about developing new kinds of knowledge graphs that are inherently spatiotemporal.
That's a fascinating idea. So, instead of just nodes and edges representing objects and relationships, you have nodes and edges that also represent locations and trajectories. You could then use AI to learn the rules governing how these spatiotemporal relationships evolve over time. It's like building a dynamic map of the world, constantly updating itself based on new information.
That sounds incredibly complex, but also incredibly powerful. Imagine an AI that could not only understand the current state of the world, but also predict how it will evolve in the future. That would be a true genius at compression, because it would only need to store the essential information needed to make those predictions.
But again, it comes back to the question of understanding. An AI that can predict the future isn't necessarily an AI that understands the future. It might just be very good at extrapolating from past data. To truly understand the future, you need to understand the underlying causal mechanisms.
And that requires the ability to reason about counterfactuals. What would happen if I did this instead of that? What are the possible consequences of my actions? That's where the ability to translate between different coordinate systems becomes crucial. You need to be able to imagine the world from different perspectives to simulate different scenarios.
Okay, let's bring this back to the brain. How does the brain handle counterfactual reasoning? Are there specific neural circuits involved? Can we identify those circuits and then try to replicate them in AI?
That's where neuroscience can really inform AI. We can study the brain's architecture, its algorithms, and its learning mechanisms, and then use that knowledge to design better AI systems. It's not about blindly copying the brain, but about extracting the underlying principles and applying them to AI.
But we also need to be careful about drawing too many parallels between the brain and AI. The brain is a biological system, and AI is a computational system. They have different strengths and weaknesses. We shouldn't try to build AI that is exactly like the brain, but rather AI that is inspired by the brain.
I think the key is to focus on the functional principles, not the specific implementation details. The brain might use neurons to perform computations, but we can use transistors. The important thing is to capture the underlying algorithms, the ways in which the brain processes information.
Right. So, zooming out a bit, what are the broader implications of this research? If we can build AI that can truly compress like a genius, what kind of impact would that have on society?
It would revolutionize everything. Imagine AI that can understand and process information as efficiently as a human brain. It could solve some of the world's most pressing problems, from climate change to disease to poverty. It could also lead to new forms of creativity, new forms of art, and new forms of scientific discovery. We would essentially be unlocking the power of human-level intelligence.
But it also raises some serious ethical concerns. If we create AI that is smarter than us, how do we ensure that it uses its intelligence for good? How do we prevent it from being used for malicious purposes? We need to think carefully about the ethical implications of AI and develop safeguards to prevent it from being misused. The creation of AGI comes with responsibility.
And who gets to decide what constitutes good? That's the fundamental question. We need to have a broad societal discussion about the values we want to embed in AI. We need to ensure that AI is aligned with human values and that it serves the interests of all of humanity.
Those are incredibly important points and a conversation for another episode. For now, bringing it back to research directions, I'm particularly interested in how we can leverage insights from neuroscience to develop more sophisticated scaling rules for integrating knowledge and reasoning processes in AI models. How can we model the hierarchical organization and distributed processing of information observed in the brain to create AI systems that combine deep learnings, pattern recognition abilities with explicit symbolic reasoning? I'm particularly interested in exploring how neurobiological principles of synaptic plasticity and long-term memory consolidation could inform the design of robust and adaptable AI architectures.
I think the ratio of knowledge-based facts to reasoning capabilities in current large language models, LLMs, reveals a potential bottleneck in their development toward AGI. More data is crucial, but the algorithms themselves may not be optimally leveraging the knowledge they're absorbing, leading to inefficient scaling. We need to find ways to make these models more efficient at reasoning, not just at memorizing.
And that goes back to my point about neuro-symbolic approaches. We need to move beyond purely data-driven approaches and develop algorithms that can genuinely understand and manipulate knowledge. I'm curious if symbolic representations combined with reasoning algorithms could potentially achieve a more nuanced and efficient form of intelligence.
And I'm convinced that brute force deep learning approaches to intelligence are fundamentally missing the point. If AGI requires the ability to seamlessly translate between different coordinate systems, like representing knowledge in terms of physical space, abstract concepts, or even temporal sequences, current deep learning's reliance on massive datasets and complex parameter tuning seems like an inefficient workaround. I think focusing on developing algorithms that are inherently capable of understanding and manipulating different coordinate representations is the key.
Well, it sounds like we have plenty of exciting research directions to explore. It's clear that building AI that can compress like a genius is a complex and multifaceted challenge, but it's also one that holds immense potential. Thanks everyone for this fascinating discussion. And thank you to our listeners for joining us on Cognitive Spirals. Until next time.
Thanks for having me.
Thank you.
Goodbye.